Thank you, Pascal. And thank you, first of all, to Ricky for organizing this very stimulating conference. So I'd like to tell you this morning about some work that I did started during a visit to Professor Kumaran's laboratory at the Indian Institute of Science in Bangalore. Kumaran was here earlier, but he had to leave early this morning, so it was done with him and his student, Anki Reddy. So what we're trying to do here, as we've heard several people mention this week, shape is an issue in granular systems. Many people recognize its importance and the need to include some effects of shape in particularly industrial applications. Yet despite that, there's really been very little work examining the effect of shape, although we did hear a little bit about that yesterday as well. But they're really relatively few, and I'll just mention a few of the more fundamental studies where people started by studying very simple non-spherical particles. Obviously, needles is the simplest thing you can think of. About 8 years ago now, Zipelius and her group examined a freely cooling state of hard needles and observed Haft's law in that system, and also the fact that equipartition breaks down in that state so that the rotational granular temperature is smaller than the translational granular temperature. And then with Pascal, we looked at a similar system, but this time in a stationary state where we're driving the hard needle. And again, there we saw that equipartition breaks down, and the degree that it breaks down depends on the moment of inertia and the coefficient of restitution of the needle. And then very recently, there's been some work involving these giant number fluctuations in driven systems of rods, which was originally claimed to be as a result of the shape of the particle. But in fact, was shown by Aronson shortly afterwards that you can observe the same effect using spherical particles. And then there have been a few other studies of vibrated rods as well. So what we want to do is really now look at a different way of supplying the energy to a system. And of course, as many of you know, this is a very clean way of driving a granular system using this boundary condition introduced by Lees and Edwards in the early 70s. And for those of you who are not familiar with it, it's boundary-driven shear, so that every time a particle crosses a boundary, an upper boundary or lower boundary, it's given a kick. In this case, it would acquire a velocity of plus u over 2 or minus u over 2, depending on which boundary it crosses. So this should supply energy, and it should lead to a uniform homogeneous state. And then we're going to see then the obvious question we want to ask then is, how do these non-spherical particles orient with respect to the flow? And are there any orientational ordering transitions in these systems? And of course, there's a great deal of previous associated work with slightly different systems, dating back originally to Ansager, who showed that for very long rods, there is the possibility of an isotropic pneumatic liquid crystal transition, okay, even without attractive interactions between the particles. And then more recently, Dan Frenkel showed that you can have the same behavior for particles of finite elongation, such as ellipsoids or spherocylinders. And then Kumaran had looked at the effect of shear on the solid fluid phase transition in the hard sphere system, and observed that indeed shear tends to suppress that first order solid fluid transition. All right, so here's then the model that we will be examining in this talk. The particles consist of two fused disks, all right, at a certain separation. And we refer to these objects sometimes as dumbbells, right? And they have, each one will have a translational velocity and a rotational velocity, right? We're going to consider them as frictionless particles, right? And they collide instantaneously. And this is the collision law that we use. Obviously, this is a very simple model. You might say we should include friction, but we're going to start by using the simplest possible collision law and see what we get there. The collision dynamics are governed by conservation of linear momentum, and here conservation of angular momentum about the point of contact. All right? Then if we use smooth particles and we say that the impulse is normal to the point of contact, then that leads to this simple formula here that we can use to calculate the impulse for any colliding pair of particles. All right? And let me just say briefly a little bit about how the simulation works, because we have to use a non-standard technique because of the fact that these are non-spherical particles. And the algorithm works in terms of an overlap function, which is simply positive if two particles are not overlapping, negative if they're overlapping, and zero at contact. For hard spheres, this leads to a particularly simple event-driven algorithm, which has been used for many decades now. All one has to do there is to define the overlap function as the separation of the centers of the hard spheres, and that leads to a simple quadratic equation which either has 2 or 0 roots, and then this can be implemented very easily using these well-known tricks of the trade. But of course, if you're dealing with non-spherical particles, then you have the possibility for an infinite number of collisions, or a nonlinear equation with an unknown number of roots. So that leads to technical complications. And one solution that has been proposed and that we used in this work is this method of retrospective collision detection, which allows us to bracket the collision times of the two particles. So briefly, the way that the algorithm works is that the configuration is advanced by a constant time step delta t, right? And in general, there will be some overlap between particles at the end of that time step. And then we rewind to find the instant of collision, right? Perform the collision using the dynamics that I just mentioned, and then rewind to the end of the time step. Right? We may have to do that several times to resolve the collision sequence. All right, so then here is hopefully a little movie to illustrate that this method is robust, and it was pleasing to find that it works for a range of volume fractions. Here, 0.4 up to really quite a dense system of 0.8. All right, so then just to introduce some geometry that I'll need to explain the results to you, we say x is the flow direction, y is the gradient direction, and then the orientation of the dumbbell will be characterized by theta. In fact, because this is a hard particle system, we can set the time scale in terms of the strain rate in this system. All right. So first of all, here's what happens then. We start with an arbitrary configuration, obviously without overlaps. We let the simulation run, and then the shear propagates from the boundaries into the system, and a steady state is attained. And what we see that, well, first of all, the velocity profile is linear, right? This exactly agrees with what you would expect, gamma dot times the position in the cell. And other properties, such as the stress, packing fraction, linear and angular velocities, these are all represented by these symbols here, are constant within the cell. In fact, there's one of these properties shows a little bit more variation. That is the angular velocity, where we can see variations up to 20%, but all the others, including the stress tensor, are very constant throughout this system. All right, so again, to understand some of the results that I'll present you, we can use this kind of dimensional argument that has been evoked several times in the meeting this week, right, which just shows us that we should expect the shear rate, the dissipation, the average dissipation per collision, and the square root of the temperature to be related in this way, even in this system here. All right, so first of all, then we can look at the velocity distributions, all right? Again, it's low packing fraction and high packing fraction, and I'm showing you on the same plot the x, y, and the angular velocities, all right, all scaled by their respective mean value here. And what we see is that to a very good approximation, these are Gaussian. This is a little bit unexpected because in other systems we see more deviation from Gaussian, but at least over the range that we looked, we don't see any significant deviation, which is kind of good news because it then means that it will be easier to develop kinetic theories for this system in just using anisotropic Gaussian distributions. All right, now if we look at the granular temperatures, all right, of course, it's expected that they should be anisotropic, and they are. So we see that the temperature in the flow direction, in the x direction, is larger than in the gradient direction, all right, and that is also larger than the rotational granular temperature that we'd observed in the simpler systems that I showed you earlier. And of course, we'd expect and we observe then that as the inelasticity goes to zero, we recover equipartition, right? So again, that's a good confirmation that this model the simulation is working correctly.
What were the different lives?
They're different packing fractions. Here's the mean angular velocity of the particle. All right, again, at different packing fractions shown by the symbol. What we observe here is that at low packing fractions, the mean angular velocity is equal to the mean rotation rate of the fluid, right, or half the vorticity. But at higher packing fractions, the particles are rotating more slowly than the local rate of rotation of the fluid. Right, and that is a little bit surprising when we look at the stress tensor, which we see again for all these packing fractions. This one is 0.7. Right, well, even there's a little bit of deviation, but obviously to a very good approximation, the stress tensor is symmetric in all these systems. Yet, despite that, the particles are rotating. So that means there's no couple, no torque on the particles, but they are rotating slower than the mean rotation rate of the fluid, and that's something we don't fully understand why that happens. All right, well, so then in the last part, I'll just focus on the orientational ordering. Again, this was discussed yesterday for a different system. And we examined this orientational ordering using this matrix, which was proposed by the liquid crystal community to study the isotropic nematic transition. All right, so it's a very simple matrix composed of the components of this unit vector for each of the particles. We sum over that, form this matrix, and then calculate the eigenvalue and the eigenvector. Right? So if the system is disordered, in fact, in an infinite system where there's no orientational order, the eigenvalue is zero. All right? And in a perfectly ordered system, the eigenvalue is equal to 1, so we can conveniently use this. Of course, it doesn't matter on the orientation. If they're ordered, it will be 1, whatever direction they're pointing in. All right. So here's the first result where we look at this orientational order parameter as a function of the elongation. All right, at different packing fractions. Again, and we see that the orientational order, as you might expect, it increases with the elongation at constant normal coefficient of restitution, right? But there's no discontinuity. It's just a continuous increase in the orientational order with increasing elongation as we move from something that's nearly like a disk to something that is two tangent disks. This orientational order increases. All right, so now here we're showing the orientational order as a function of the inelasticity, right? And that increases as the collisions become more inelastic again. But we can use this result here to understand what happens in the non-sheared system, right? Because if we go back to this kind of energy balance relationship here, all right, if we consider the case where En goes to 1 for an elastic system, we can consider that to be equal to a system with a 0 shear rate. Okay, so En goes to 1 corresponds to an elastic system with no shear. And so what we see then in all cases there is that there's no orientational order, all right, in such a system, right, which is expected for this system based on a theoretical analysis that another group did some years ago, right? There isn't expected to be an isotropic nematic transition in this system without the shear. All right, so now we can look in more detail about how these particles are oriented with respect to the flow, right? Again, it's a medium elongation and a high elongation. And what is observed then is that, of course, at low packing fraction, these curves approach a flat distribution, right? So there's no preferred orientation. But with increasing packing fraction, they become more peaked, okay, with a strongly preferred orientation. And that's the same at low and high packing fraction. And we can then try to answer more precisely what is that preferred orientation? How are these particles oriented with respect to the flow? So to get that angle, we just take the components of the eigenvector and compute the angle of orientation, right? So again, well, this is showing how that depends on the elongation for different packing fractions. This is the lowest packing fraction. Sorry I didn't put the values on here, but I think this is a 0.1 or 0.2 packing fraction, right? We see there that the orientation, the preferred orientation, is at an angle of theta is 45 degrees, which is the extension axis in this flow geometry. And in fact, that was a result first observed by Maxwell, right? Who examined the alignment of particles in fluids, right? So we do see that certainly at low packing fraction, there's a preferential alignment along the extension axis. As the packing fraction increases, the particles tend to orient more along the flow direction. All right, and then finally, we noted that we can perform this Fourier expansion of these orientational distribution functions here, right, about the maximum angle, all right, and we only need to retain the cosine terms in that case, and we can show that the first coefficient here is related to the orientational order parameter by this result here. And what's interesting is that except at the highest packing fractions, all right, so below about 0.7, that is, we can reproduce these simulated distribution functions just retaining the first term of this series here. All right, and in fact that's what the lines show is that fit, right? And it's really very good except in this case here. All right, so that's the end. I mean, obviously it's important to understand how particles are oriented non-spherical particles are oriented in flow, because that will affect the rheology of the flow as well. And what we've seen here is that there's, in this system at least, there is a continuous increase in the orientational order parameter, all right, but no isotropic pneumatic transition. And that we see the orientational distribution function increases in a self-similar manner as the volume fraction increases. So what we plan to do now, obviously the next step here, the interesting thing would be to look at the three-dimensional system, probably of ellipsoids, where it's known that above a certain aspect ratio there is an isotropic pneumatic transition in the absence of shear, right? And so then we can see for that system if again the shear will suppress or enhance that transition. So thank you for your attention.
Yeah, I may have misunderstood you, but I was
Yes.
very surprised by
Yes.
the fact that the stress
Yes.
tensor
Yes.
was isotropic,
Yes.
even though the
Yes.
particles were rotating.
Right.
It's
Symmetric. It's symmetric. The stress tensor is
was
symmetric.
was symmetric.
Yes.
Of course, yes.
Yes.
Well, do you have any explanation as to
No,
that?
I'd be delighted if anyone could offer any explanation here, but it does seem strange, yes.
But obviously, it's the Schlizer-Edwards boundary condition which provide the energy input, but
Yes.
but those boundary conditions are not an applied stress. Are not put in as an applied stress.
No,
That's right.
exactly, right.
Thanks.
Comment?
In your simulation method,
Mm.
don't you have the kind of collapse problem, inelastic collapse problem? Do you have a cutoff or event-driven?
I was expecting to see that, but we didn't for the ranges of packing fraction and the inelasticies that we were using. No, so it wasn't a problem in this system.
More question?